Let's get started. All right. So we have a problem set through today, and the next one will be available soon. I haven't received feedback from everybody, but almost everyone, so I'll make a decision about office hour. It looks like if we want to have office hours on Monday, the only time that would be available would be before 11 o'clock. So like 10 to 11 is something that would work. I'll take a look. Alrighty. So last time we were talking about a very important problem. We were talking about the problem of how do we, in our quantum mechanical description, discuss the coupling of a charge to an electromagnetic field. And at the moment, and pretty much throughout this course, we treat the electromagnetic field classically. Of course, the field itself is a quantum degree of freedom and should be quantized, and we should talk about quantum electrodynamics, a quantized electromagnetic field. But under certain approximations, which we won't really discuss, but we'll just say that there exists a regime in which it's fine for us to treat the field classically. All right? So to get there, we started with the classical description, where charges move under the influence of electric and magnetic fields according to the Lorentz force law, and that those Newtonian dynamics are derivable in a Lagrangian and a Hamiltonian formalism. Okay? So we wrote down what the Lagrangian is and the Hamiltonian. And given the Hamiltonian, we can then quantize by just now saying that the canonical coordinates, position, momentum, become the canonical position and momentum operators. Okay? And so this is our Hamiltonian for the system. For a charge, mass, and moving in electromagnetic field. Okay? And one of the things that's very tricky about this is that the canonical momentum is no longer just NV. It's NV plus a term that depends on the vector potential, okay, at the position. And a very important aspect of this is the issue of gauge invariance. So, for example, if we make the transformation on the vector potential, that we transform it according to the gradient of some scalar field, then the magnetic field is unchanged, and classically there's no way to tell the difference between this vector potential and this vector potential, because they lead to exactly the same equations of motion. The motion of the charge is the same. Okay? And we demand thus that the physics be gauge invariant. It should not depend on a choice of gauge. We choose the gauge we like for convenience mathematically, but at the end of the day, the physics doesn't depend on the choice of gauge. Okay? So that kind of gauge invariance and gauge transformations must be part of the quantum mechanical description as well. And the way that we achieve that is by having a unitary transformation on everything for different gauges. Because if we transform everything unitarily, we won't change in any way the prediction of any measurement outcome. Okay? Because unitary operators preserve the inner product. And we achieve that by just a simple unitary transformation depending on whatever gauge function we have. All right? So under under that transformation, the Hamiltonian does what we want. The Hamiltonian is now a Hamiltonian with a new vector potential. It doesn't do anything to the scalar potential for the way we're writing our gauge transformations at the moment. So the vector potential gets shifted by the gradient of this scalar field. That's what we wanted. And the wave function in the position representation just gets an overall phase, which again doesn't change the predictions of anything. But that overall phase is a function of position. Okay? And as we discussed at the very end of lecture last time, we can kind of turn that argument on its head. We can say, it must be the case that if I take the wave function and transform it in this way, I don't change the physics. Because we can always put an overall phase in front of the wave function without changing any of the probabilities for any outcome. So it must be the case that the physics is invariant under this change of the wave function, okay? And if that phase is position dependent, then the only way that I can make the Schrödinger equation the same is to shift the momentum in this way with this extra term here. So that is a way of arguing that quantum mechanics insists there must be something like the vector potential. If we want gauge invariance, then we must have a vector potential. And that's why in modern field theory, we talk about the way in which elementary particles couple to fields as, if they do it in this way, as gauge fields. And it's really the foundation of modern quantum field theory. Which hopefully you'll learn someday. All right, so to continue with this line of thought, let's just talk for a moment. Let's talk about the problem of a free particle in a B field, or in a magnetic field. Okay, so let's forget about the scalar potential for the moment. Okay? Now, so there's my Hamiltonian. And I want to look at the dynamics of this system. I can automatically write down a solution to the Schrödinger equation. Because a solution to the Schrödinger equation in the position representation is just this. Sorry, again, I have all my cues and so forth. In other words, I can gauge away the whole vector potential, right? This is like my chi of x. If I take the gradient of that function, I get the vector potential, okay? So that's interesting. It's a little, I'm writing this a little bit of, I mean, what path am I talking about here? This is a path that goes from some x0 to some x. So this is really not quite right. I really have to sum over, it's really, I should really think about this from a kind of path integral perspective, where I sum over all possible paths that get me from one to another. Okay. Okay. So that's fine. It's interesting. But there's, as you probably have heard about, there's a very profound implication of this. Okay. So we said the overall phase here doesn't affect any. The overall phase doesn't affect any of the physics, any of the predictions of what measurement outcomes I can have. But relative phases do, right? And that led Aharonov-Bohm to consider the following Gedanken experiment in the, gosh, when was that? Like 1960, late 1950s, I forget. Yeah, when that was. It was before my time, older than me. To consider the following kind of Gedanken experiment. Suppose I have an electron. Okay, I have a point source of electrons, and I'm going to send it through a double slit. Okay? So I have a double slit. And the screen. Okay? The electrons can, they're safe to this position, there's some set of paths it could take to get to that position. Okay? Now, suppose that right behind this screen, I put an infinite solenoid. Okay? So it has a magnetic field coming, say, out of the board, but it's infinite in length. Okay, so there's no fringing fields. No fringing fields. All of the magnetic field is inside that tube. There's no magnetic field outside that tube whatsoever. Okay? Now, you all remember from your 405 or equivalent what the vector potential is of a solenoid, right? Prelims are coming. It's not zero. The vector potential is not zero outside the solenoid. It's a little exercise for you to think about it. Okay? The vector potential is everywhere in space. Okay? But the curl of the vector potential is zero outside, completely zero outside the solenoid, and it's uniform inside the solenoid. Okay? Right. So now, what do we have? Well, if I use this solution, let's call this x0, and this x. Okay? And I want to know what is the wave function. Well, it's a superposition of paths. Here are two particular paths that superpose to give the total wave function here. So there's a path I'll call C1, and there's a path I'll call C2. This is a little electron. That's the charge. I'm always going to call E a positive number. Okay? E is a positive number. The charge of the electron is minus E. It's confusing. Books go all over the map on this, and I always get the signs wrong because of that. Okay? Fine. So, what does this say? This says that the total wave function here is e to the minus I, what I'll call C1 at x, at 0, or psi x 0, plus e to the minus I C2 psi x 0, where C sub I is the integral over contour I e over h bar c, the integral from x0 to x over the contour I, a of x dl. Okay? All right. Now, here's, of course, what's exciting. If you look at this, let's factor out one of these phases, because at the end of the day, it's only relative phase that ever matters in quantum mechanics. We can never observe directly a phase. It has no physical implication. It's only the relative phase that ever has any physical implication in terms of the prediction of a measurement outcome. Okay. Where delta is equal to the integral over C1 dl minus the integral over C2 dot or a dot or dot x, right? The difference in those two. So I have two paths. The path that goes from here to here, and then the path that goes from here to here, right? When I subtract it. And that is thus equal to the closed contour integral around the path between those 2 points, a dot dl. Okay. Now, this has to be, this is observable. That is to say, whether I have constructive interference or destructive interference or something in between depends on what the relative phase between the two paths are. And in principle, I can turn on and off the solenoid and see whether or not the fringes shift or not.
Did you say that the curl of A was 0?
I didn't say that.
I thought,
I said the curl of A is 0 outside.
Outside.
Because the magnetic field is 0 outside the solenoid. So classically, there is no force on the electron.
Okay.
Classically, the force on the electron equals 0. There's no magnetic field outside. But there is a vector potential outside.
But it's conservative?
Well, don't you worry me, it's not, remember, magnetic fields are not conservative
What about
fields.
the A field? I'm sorry. Is the curl of A was 0, if I understand that correctly? Or no, I'm not understanding that correctly.
The curl of A is 0 outside,
The
but
field,
it's
okay.
not inside.
Okay, okay.
So it's true that the curl of A is 0, but that's not the same thing as saying it's a conservative force.
Okay.
A conservative force is the curl of F is 0.
Okay, so that's not necessarily 0 then?
Right, so
Okay.
here, that is of course the whole story.
Okay.
So this is not 0,
Okay.
because the vector potential along these two paths is not 0.
Okay.
And in fact, the closed contour integral of the vector potential is not 0. What is it? We can use Stokes' theorem, which tells us that the contour integral around the closed contour is just equal to what?
Double integral of the curl of A dot dA.
Right. So this is over the surface
That
that's bounded by this, in this case, this surface, oriented according to the right-hand rule. So there's a normal here, depending on what I have. So it's curl of A dot n hat dA. That's Stokes' theorem, right? And this, of course, is D. Inside the surface bounded by that contour. And this is just a flux of the magnetic field through that surface bounded by those contours. So this is fascinating. This is saying the following. There's no classical force on the electron. The solenoid is infinite in length. We'll come back to that in a moment. But let's just think mathematically. This solenoid is infinite in length. There's no fringing field. There's therefore zero magnetic field outside this region. The electron doesn't penetrate into that solenoid and feels no force. Nonetheless, where it lands on the screen depends on the existence of that flux. That's known as the Aharonov-Bohm effect. And it's extremely interesting, subtle, and complicated, and in my view, still hard to completely wrap our brains around and explain. Yeah.
What about this when we only included two paths?
Yeah.
When we only broke it into two paths like that?
So, of course, we really need to do a path integral over all the paths, right? But it's still, so one has to ask the question, this was, in some sense, part of the, this is very controversial when it was kind of dismissed, I think, my reading of the history of it, for decades. Because A, you didn't have infinite solenoids, so there was definitely fringing fields, and there was some thought that these fringing fields were really responsible for this effect. Or moreover, the electrons could penetrate in, and that there'll be some interference between what happens when the electrons penetrate into the solenoid. But in the early 1980s, mid-1980s, something like that, when mesoscopic 2D electron gases in materials were being developed, thin films and things like that. Experiment was done. There's a famous experiment from Tanimura, which, let me show you. I'm going to come back to have some further explanation of this. So let's turn this on. Oh, I need to get the doohickey. Let's hope this works. Something happened. could be. I'm wondering if this thing is broken. Let's see. I hope not. Oh, great. Now I lost my picture. Stupid global Wi-Fi.
You made the latter here? Yeah.
Oh, well, this is going to be. Let's see if this works.
Check your history.
No, it's just I'm not connected to the stupid internet because of the local Wi-Fi. Let's hope this works. It's hopeless.
There you go.
All right, that's what I wanted to show you. All right, so this is a famous experiment from Tanimura, where what he did is the following. He created a toroidal magnet. So this is a superconducting torus, and there is magnetic fields that go around in a circle there. And he did a measurement, and the leakage outside that torus is tiny, completely negligible. There's almost nothing that gets out of this thing, okay? So there's no magnetic field in the hole, there's no magnetic field outside, there's only a magnetic field inside this torus, okay? So we can think about a cross-section through this thing, and it's kind of like our picture of the infinite solenoid. And then he shot electrons through this system and had a kind of local oscillator which interfered those electrons with themselves, depending upon whether they went through the center of the hole or outside. And what he saw was this. And what you see is that there is a pi phase shift of what the electron interference is inside the hole versus outside. So there is no doubt the Aharonov-Bohm effect is real. Yeah.
So, I mean, so this print pattern gives you information about whether there's a field or not inside,
Yep.
but classically there's no interaction.
Classically, there's no force.
So what is the mechanism of interaction then between
Right,
the
okay.
field?
So that is an excellent question. So how do we understand this? It's not so there are different ways that I would say you hear an explanation of the Aharonov-Bohm effect. I'd say the most common thing that's said is that thing that I just showed you, this effect, is proof solid that the vector potential is a physical field. There is a local interaction between the electron and the vector potential.
Okay.
And even though, and that, local interaction, which we see here, gives rise to this phase, which affects where the electron is, okay? And that sounds reasonable, bless you, except which vector potential does it feel?
All of them.
Well, I mean, if it's being affected by the vector potential, well, the vector potential is not a gauge invariant property. If I make a transformation of A goes to A plus gradient of a scalar, exactly the same effect. Because at the end of the day, what this phase is depends on the curl of A. The phase depends on B. It doesn't depend on A. Well, it depends, of course, on the flux of B. But the physics, as we demanded, must be gauge invariant. Where the electron lands can't depend on what choice of phase. I mean, choice of gauge, yeah.
What if it was outside of the magnetic field, was on the other side of the contour? So it was outside of the contour?
Yeah.
But the magnetic, or the vector potential is still everywhere, but then it wouldn't have the effect, would it?
Well, I mean, the effect is always whatever the flux of B inside determines what that phase is. So even if it filled the whole thing, it would but it wouldn't have the weirdness. So, you know, it would, if we had, in this case, if the electron were able to penetrate into this, there would be a phase shift there that depends on that flux. Of course, it experiences the B in there, so it would still be there. But the craziness of the Aharonov-Bohm effect is that even in situations that you rig it up that the electron can't penetrate into the region where the B field is, there's no probability for the electron to be there. It still kind of knows about the B. So one way to say it, as I say, is to say, look, what the electron is feeling is the vector potential. The vector potential is non-zero outside, and it's the vector potential that affects where the electron is going to be found. Okay, that's a local interaction. Another way to say it is, well, no, quantum mechanics is in some sense non-local, and the electron knows about the existence of the B over there, even though it didn't go over there. Now that you have to be extremely careful about, because you better not have causality breakdown, Einstein causality, where I could signal something about one point in space-time to another point in space-time with it going faster speed of light. Now, you can't see that in this thing because, of course, this is a static situation. There's no, and you have to think about the time-dependent problem where you turn on the current and make and establish that, and that's a much more complicated business about how it could signal. I've never seen that analysis done carefully myself. I don't know how it would work. But yet there's one last way of kind of interpreting this, which is say what's physical actually are these loop integrals. That's a kind of topological effect, that somehow the topology of the system, which is a kind of global property, is affected by the existence of the B field. There's a kind of hole in the space that is affecting the whole notion of what the space-time is by the existence of that hole. And any loop around that hole has a different property than loops that are not around that hole.
And this explanation doesn't assume that A is a physical.
That's right. Because at the end of the day, the phase we see depends on B. It can't depend solely on A, because which A? Now, I was doing a little bit of research on this over the last few days to educate myself, to try to educate you guys. And there are, some papers that talk about, well, actually, maybe there's one true gauge. There's the true gauge that is the real physical A that actually is existing in the world, and all the other gauges are, physically equivalent, but what you're really sensing is there is a true gauge. Who would know? How would we know? But there, all I can say is it's a real effect, and it's one of the strangest things that we see in quantum mechanics. Yes, Steve?
Okay, so maybe I'm thinking about this too classically, but I'm thinking, okay, so the A field's, real,
Yep.
and the electron interacting with it
Yep.
through electromagnetic interaction mediated by photons or something. Is that a bad way to think of that?
What do you mean via photons?
I don't
It is
know.
photons.
I mean, okay.
So, I mean, so here's what I would say. The interaction is described here. Okay, let's look at this Hamiltonian. Let me write it out explicitly. This is p squared over 2m minus q over 2mc p dot a plus a dot p plus blah, 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 a squared term. Okay? So, here's the interaction. The vector potential locally talks to the charge through an a dot p interaction. It's not through the Lorentz force. It's through this term in the Hamiltonian. Okay? And thus, the electron locally, vector potential, it's right here, right by me. I can sense it. There's a local interaction right here between the electron and the electromagnetic field through this interaction. And it is through that that we get this phase, and it is through that that we get this observable phase shift.
Okay.
I would say that is the prevailing view.
Okay.
That people say, Aharonov-Bohm proves the vector potential is a physical field. You will hear lots of people say that. You've probably heard your professors tell you that. I take issue with that because which A is it smelling? Is it smelling that A or that A? How would we know? So what physical field is affecting the phase, the probability that it lands at this? There's no way I could tell whether the electron smelled that vector potential or this vector potential. Both of them lead to the same physical effect. So from my perspective, this is not physical. So it's still, and the way I think it makes sense is to think it's really some kind of topological effect. Something about the nature of space-time itself is affected by the existence, and it's more global than local problem.
Hell of an effect, it seems like.
All right, well, it's for you all to think about some more and to come to your own opinions about it. All right. Very good. That is one of the coolest things in the world. Right. By the way, I guess I left out this humor. So phi naught here is what I'm calling h bar c over e. This is the fundamental quantum of flux. And it pays a very important, it's got the units of flux, right? Because this is a phase, this is dimensionless. So the ratio of this to the flux quantum is dimensionless. And it plays an important role in the theory of superconducting, type 2 superconductors, in the saying that flux has to be quantized, because it must be the case if you have a coherent wave function that goes all the way around a flux, it must come back to itself in units of 2 pi. So flux inside a superconducting material is quantized. That's how superconducting, so you may have heard of a squid, a superconducting interference device, it all works through the Aharonov-Bohm.
checking the magnetic field's quantized too then, or?
Yeah, the flux is.
The
This
flux,
is the
not
flux.
the, okay, okay.
Yeah. All right, very good. So let's now talk about a particular problem. Let's talk about the problem of a charge in a uniform magnetic field. Okay? So again, I'm going to take the electric scalar potential to be 0. And we can write down the vector potential. Now there's many ways, we know. It's not a gauge independent quantity, but there's a convenient gauge that we typically work in when thinking about static, and that is this gauge. Okay? So I claim, so this is my magnetic field, this is a constant. I'm sorry, that's position. So this is A, excuse my, as a function of X, is that. So this is.
See now the X?
This is the position. There's no C.
Okay,
That's a cross product.
Okay, I see.
Okay, so A sub I is minus a half epsilon I j k x j dk. Okay, sum over j, sum over k. B is a constant. This is the position at which I'm observing the field. Okay, I claim, and I'm sure you did this in your statics class, you just don't remember, that the curl of A is B. This is a good exercise for those of you playing around with your epsilon ijks and Levitt-Chibita symbols. Give it a shot. You can prove it for yourself. Okay? All right. So let's see. So now my Hamiltonian for this problem is 1 over 2n p minus q over c a squared, which is equal to, as we wrote down over there, p squared over 2n plus 1 over 2n p minus q over 2n c p dot a plus a dot p. And then we have plus q squared over 2n c squared a dot a. Okay, and now we plug it. Let me get my notes. Right. Okay. So let's take a look at these terms. So P dot A plus A dot P is equal to P dotted into, or minus a half P dot X cross B, and these are operators, plus X cross B dotted into P. Okay? Given that form of the vector potential. All right. This term over here, we can switch the cross and the dot and write it like that. Right? Can you recognize this? P cross position.
Oh, is it a angular?
Angular momentum.
Yes, yes.
Well, see, it's minus the angular momentum, right? R cross P, I'm writing is X cross P. So this is the orbital angular momentum with our minus angular. Right? And with a little bit of manipulation with all these cross products, again, this becomes exactly the same thing. So this becomes equal to L dotted into B. Yeah, that's good. All right, very good. So let's just look at that term first, and we'll come back to the other one in a moment. So that means that, so we have a term here. Let's call this, I'll call this H1 and this H2. This is the kinetic energy over here. So what is H1? So it's equal to minus Q over 2mc L dotted into B. This has a physical interpretation that we can glean and understand from quantum classical dynamics. Okay? This, I claim, is the magnetic moment associated with orbital motion of the particle. Okay. How do I see that? Well, let's just consider classically for a moment. Let's just suppose, as an example, suppose I have a charge going around in a circle. Okay? So this is a circular motion. Periodically with some angular frequency omega. Okay? This is a current loop. It has a current I. That current is equal to 1 charge per oscillation period, right? And that oscillation period is 2 pi over omega. So that's the current. If I have a current loop, then I have a magnetic dipole moment. Okay? Which we'll call mu. And that magnetic dipole moment is equal to the current times the area of the loop in SI units, and it's over C in CGS units. Okay? In the direction normal. According to omega. Okay? All right, so now let's plug all of that in. The current here is Q omega over 2 pi. The area of the loop, let's say it has a radius r, is pi r squared. And then I have C. And then in the normal direction, that's the direction of omega. Okay. this is thus equal to Q over 2C omega R squared. Sorry, just was thinking about one thing. Oh yeah, okay. Very good. All right. So, if I multiply, if this charge also has a mass, and I multiply this top and bottom by the mass, then you recognize this. What is that? It's the angular momentum, right? And VR. V is omega R. Okay, so this is the angular momentum. And so we get exactly what we had over here. Okay? This is general, it's not just true for a circular motion. If you classically write down the expression for the magnetic dipole moment for moving charges that have current, this is the general expression of a charge that's moving in some way, then this is its magnetic dipole moment. Okay? And we just quantize it, so just put it on that. And that we see that comes out. This quantity here is known as the gyromagnetic ratio. So mu, and we sometimes call that gamma, is gamma times L. Okay? So this term H1 is minus the orbital magnetic dipole moment dotted into the magnetic field. Okay, that's what's there. That came out of the Hamiltonian. And this is what we would have written down if we didn't know anything about vector potential and all that. We'd say, what's the interaction of this charge in the magnetic field? Say it's minus mu dot v, where mu is the mu associated with the orbital motion. This particular Hamiltonian is known as the paramagnetic interaction. Why? Well, in paramagnetism, if you have a material that's paramagnetic, then if you have a magnetic field here, the lowest energy configuration is the one where mu is in the same direction as B, right? And so it tends to try to increase the magnetic dipole moment along the direction of B. That's paramagnetism. Okay. Now, one piece of my notes here that I'm missing, so excuse me for a second. Okay. Oh yeah, okay. I missed that. I'll come back to that in a moment. I see where it was. I forgot to say. Right. What was I going to say? Oh yeah. So let's think about this, what the strength of this interaction is at atomic scales. Okay. So for an atomic scale, we talk about atomic units, and I will re-emphasize this next lecture, but we have the electron, E, that's our charge. Of course, it's minus E, but this is sort of the characteristic size, is q. And what would you say the characteristic angular momentum is? Yeah. Okay. So there's a characteristic magnetic dipole moment, according to this thing. Mu atomic is E h bar over 2 mc. Okay. And this is known as U sub B. It's known as the Bohr magneton. Okay? And what the heck are its units? Well, who the heck knows what the units are of magnetic dipole moment. But we do know that the mu b times b is an energy. Right? And so the units I always know this is if I write this in terms of frequency by dividing by Planck's constant. So now this is a frequency. It's h nu is energy. So the units I always know for frequency is that UV in units of Planck's constant is 1.4 megahertz per Gauss. That's what a good atomic physics experimentalist will know. You put on 1 Gauss, you get about a megahertz of shift. All right, now, you know what, before I get to this term, there was one thing I wanted to say that I forgot to say that I want to come back to over here to get a better understanding of what's going on over here. One of the questions you might ask yourself is, what the heck does the canonical momentum mean relative to the kinetic momentum? I mean, we just added that one. What does it mean? Is there any physical understanding? But let's see what it is in this particular case. So let's look at what the canonical momentum is. It's mv plus q over c times a. Okay, what is it for this particular case? Well, it's equal to m x dot plus, or in this case, I guess minus q over 2 mc x cross v. All right, so how do is there a physical understanding of what this is? Well, this thing over here I can rewrite this in the following way. Omega L is equal to minus Q over 2 MC. Is known as the law of forgiveness. How do I interpret this? This says that the canonical momentum is mv plus m times this. Any guess, any thoughts about that? In any way look familiar from classical dynamics? Well, what if I were to say I went into a rotating frame that's rotating at frequency omega? What is the momentum in that frame? That's this. So this is the momentum in a rotating frame. It's not an inertial frame, it's a rotating frame. And the fact that we can get the dynamics of charges this way is known as Larmore's theorem. Larmore's theorem, and it's a good way to kind of think about it, says that the Lorentz force is equivalent to a Coriolis force. That's to say, if I'm on a merry-go-round and I throw a ball and I see it twist, that looks just like a charge in a magnetic field. The force of a charge in a magnetic field is equivalent to a force in a non-inertial reference frame. Because it's velocity dependent, obviously, right? Because it's got to be. So one way to, in this particular problem, a way to understand what the heck the canonical momentum is that it's the momentum in the rotating frame.
But then, is it an observer?
Well, it's a gauge-dependent thing,
Yeah,
right?
so
And so it's in some sense not observable. Right? Gauge-dependent quantities are not observable. Okay, that was a side I meant to say when we introduced it, but let's come back over here. So with the paramagnetic interaction, you may remember that another kind of interaction of charges with magnetic field, which is known as diamagnetism. Yeah?
But then, going back just to that point, I guess the momentum is observable, right? An observable quantity. But if you go to a rotating frame, so what's about the going to the rotating frame that all of a sudden makes it unobservable?
I would say that as it stands, that is a gauge. I could write many different gauges that would give that exactly the same physics, but would give different canonical momentum. So inside, I mean, to think about, you have to ask, I don't really know precisely the answer to this question here, but you have to think about what measurement you're actually doing. To talk about something is unobservable is in my view, too bold of a statement. The question is, what are you measuring? And what I claim is whatever you measure is observable.
Yeah.
And whatever you measure, I claim, will be gauge independent. So you come up with an experiment and we'll see how it works. That's a cop-out, but that's the best I can do. All right. So let's continue here and just talk about this last bit, which is diamagnetism. What's diamagnetism? Well, you remember Faraday effect and Lenz's law. So suppose I have a charge moving around, and all of a sudden I turn on a magnetic field. Okay? So there's magnetic field, but I have to turn it on at some point, and it changes in this direction. What's going to happen?
The charge will slow down.
Right. In fact, it's going to go in the opposite direction in order to counter the changing flux. That's the Faraday effect. And Lenz's law tells us that the direction of the induced magnetic field is always opposite to the way the flux is increasing. So in fact, there's going to be an induced magnetic field this way. Okay? And that induced magnetic field then makes an induced, so there's an induced current, which is going in the opposite direction. And that induced current makes an induced magnetic dipole moment that's induced by the magnetic field. Okay? It has exactly the opposite effect as paramagnetism. Okay? And the induced, the Hamiltonian to the induced is about this half it. I claim, I'm not going to go through the algebra here, that this is H2. That other term that I didn't write down, that comes from A squared, is the diamagnetic term. Okay? It's in the notes. Now, how big is this effect relative to paramagnetism? Well, let's look at it at the atomic scale. So at the atomic scale, these little loops here is the radius of the loop is something like the Bohr radius, a half an angstrom. Okay, so I've got my electrons kind of going around the proton, and I put these magnetic fields through them. The question is, does it speed up the electron or slow it down? Right? So the relative scale of the paramagnetic versus the diamagnetic term is basically, we can show the diamagnetic versus the paramagnetic. The flux quantum, the flux of the magnetic field going through this loop versus the flux quantum. That is to say, whatever magnetic field is, pi a squared divided by that. That's something we can show. This flux quantum is the one we wrote down over there. It's the kind of the ratio of the strength of the two. So now you have to ask yourself, how big of a magnetic field do I need to put through this such that this magnetic field, with this being the Bohr radius, this flux is on the order of the flux quantum? Well, I didn't tell you what any of these things are, but that number is that this is of order 1 when B is on the order of, according to my calculation this morning, if I did it right, I'm not sure, but I think it's right, on the order of 10 to the 5 Tesla. Forget it. In almost any experiment, we completely ignore the diamagnetic term. That's why you probably even haven't heard about it. You have to have extremely strong magnetic fields before this affects atomic spectra. Now, that's not true if for example, it does affect things like two-dimensional electron gases in superconductors, where electrons can move in very big loops. The diamagnetic term matters a lot in there, and it's all about the things that you might have heard about recently: topological insulators, anyons, all of that stuff. This stuff matters, but when we're talking about atomic spectrum, forget it. All right, so the last bit on this topic, what about spin? We talked about the coupling of the electron or a charge to the field by thinking about the motion of these particles and how it coupled to the field. But what about spin? Well, that's a tricky business, because really, to really talk about fundamentally how spin interacts with electromagnetic fields requires relativistic quantum dynamics, because spin, it turns out, is deeply tied into symmetries, relativistic symmetries. So if we really wanted to do that, we need to talk about the Dirac equation. And it was really one of the great triumphs of early quantum theory development. The Dirac equation predicted the fine structure in the spectrum of hydrogen, which, as we will see, is really a relativistic correction to the non-relativistic hydrogen atom. However, we can get at this in a kind of first relativistic correction to the non-relativistic theory using a trick of Pauli's. So Pauli, who is, of course, had fundamental contributions in the whole theory of spin, of Pauli exclusion principle, etc., formulated a phenomenological description that was soon seen to be, so there's a wave function associated with spin up and a wave function associated with spin down. Okay, so this is a representation in the tensor product space, okay, where this squared is the probability density to be spin up, and this squared is the probability density to be spin down. Okay, so now what Pauli did is consider the following thing. Consider a free particle. The Hamiltonian for this system is this. Kinetic energy on the motion, there's no effect on the spin. However, you can rewrite this in a very clever way. How do I see that? Well, there's a few ways to see that. Remember, where this dot product is really the tensor product. So this is sigma x. Now, it depends which side of sigma. It doesn't really matter whether I write it on the left or the right. I'll just do it like this. Oops. And this squared is sigma x squared tensor px squared plus sigma y squared tensor py squared plus tensor z squared. And each one of these things is the identity. This is the identity. This is the identity, and this is the identity. So that's that. Yeah?
Why don't you have cross terms?
Yeah, they all vanish. We could see it in the following way. So here's another way, and then this is sigma I, sigma j, pi, pj. Sum over I, sum over j. Right? This, we remember, is what? It's 1 if they're equal, and it's equal to I epsilon ijk sigma k if they're unequal. Okay? So this is equal to p dot p, the identity, and then I get plus I, the cross product of p with p, dotted into epsilon, which is 0. Okay? So that's cute. So this is what he,
Is it divided by 3 or?
no, because I have all three, x squared plus y squared plus z squared, that's p squared. So that's is. All right, now, here's the cool part. Gotta finish this, so I'm gonna trudge ahead. How do I now couple this to the electromagnetic field? What Pauli said was, to couple to the magnetic field, I'm going to make the substitution P goes to P plus, in this case, with the electron, minus E over C A. That's the transformation that we made on the canonical momentum. Okay? So I do that, and I get H is sigma 1 over 2m sigma dot P minus E over C A squared. Okay? Now I do exactly the same thing that I did over here. This is now going to be P minus A, and this is going to be P minus A. The terms that are P cross P go away. The terms that are A cross A go away. But the terms that are P cross A and A cross P don't go away. So this becomes, using that exact same algebra, minus E over 2 MC P cross A plus A cross P dotted in, or sigma dotted into that. Okay? All right, now what? How do we interpret this? Well, we can interpret that by going into the position representation. So this is an operator acting on stuff, right? So let's see what its action is on a state by looking at its action in the position representation. Okay? So at P cross A plus A cross P acting on a state in the position representation. That is equal to H bar over I curl of A times psi plus A curl, or yeah, cross the gradient of psi. Yeah?
Do we not need to think of it with the spinors?
That's all out here. When you do that vector algebra, what you find is that this is equal to the curl of A times psi, which is B. So, I forgot my I. It's I times that. That's good. I was going to get rid of that I otherwise. And so, what do I get? I get P squared over 2m. The i's cancel, minus E H bar over 2mc sigma dot B. Look at this. This looks kind of like what we had for the paramagnetic interaction. What is this equal to? This is equal to minus E over 2 MC. No, I get rid of the 2. E over MC S dot B, where S is H bar over 2 sigma, right? So this is very important. This looks just like what we had for the orbital motion, where we have the interaction that looks like minus mu dot B. So we have a new interaction here, minus mu spin dot B. And I got the sign wrong somehow. This really should be a plus. I'll have to go through that somewhere. It really should be a plus. I don't know where I screwed it up. But mu of the spin is equal to E over MS.
No two.
MC. Right? Which is equal to,
I think that should be negative, a positive I H bar, not a negative, not H bar over I.
I don't want to track that minus sign down because I want to track it to the most important physics. What is this? This is minus E over H bar 2MC S over H bar. This is the Bohr magneton. Okay? And then we have this extra factor of 2, which we call the G factor. So, from this Pauli construction, we see that there is a coupling of the spin to the magnetic field through a magnetic dipole interaction. There is an intrinsic dipole moment associated with the spin, but it's not just what you would have expected. This is twice the usual gyromagnetic ratio, which we had over there. And that extra factor of 2 is coming from the fact that this is not orbital. It's something else. It comes from the Dirac equation, but we see it explicitly here. And so what we have then totally, for our total interaction with the magnetic field, is we have kinetic energy minus mu orbital dot B minus mu spin dot D plus diamagnetic, where mu orbital for an electron is minus the Bohr magneton, L over H bar, and mu spin is minus 2. All right, very good. Thanks for bearing with me. Got down that minus sign, but what we will do next time is the hydrogen atom. I'm around, yeah.